I'm Mike Crabtree. Today, I'm going to be talking to you a little bit about the communication subsystem that goes inside of a satellite. Communications is something, unfortunately, the topic itself, it's like that picture of the iceberg we've all seen, right? A lot of times, all we care about is just the tip, but there's this whole thing underneath that goes behind it that makes it work. And the tough part about communications is a lot of the times we like to just hyper focus on sort of the pieces we understand about it, whereas we kind of ignore the underlying functions that really move to make a communication system work aboard a satellite. And so what I want to do here, hopefully the purpose that I'll reach today is that I can help you understand, at least get some cognizance of what exactly that underlying mechanism is that makes communications work, and give you a more holistic understanding of why it is that you should care, first of all, about satellite communications, and also how can you design your communication subsystem to meet your needs and do it in an intelligent way. The purpose of a communication system is to be able to facilitate data exchange between the ground and your satellite. This is important for a myriad of reasons, but also it's the entire point of launching a satellite, right? It's like you launch a satellite, it's doing some job, you need to be able to communicate with that satellite. If you can't communicate with it, what's the point? It's just a piece of orbital junk. And we've got enough pieces of orbital junk out orbiting the Earth as we speak. We really don't want that. And so communication system is definitely important. Some things that we consider, right, with communication systems is, first of all, selection of components, so hardware, software, stuff like that. But also we look into the complexity of the design, right? Is this radio box that I buy, is it something that I think is plug and play, or is it something that's going to take a lot of time and a lot of effort to program up and make work? These are all things that are important, and unfortunately they're things I've seen time and time again. Many individuals, not just students, I've seen industry experts just not take that into account. They just ignore it and they just think, oh, I'm purchasing this thing, it should just work. Don't assume that. The way that radios work fundamentally is they talk using radio waves. Radio waves are electromagnetic waves that permeate a field that surrounds all of us throughout all space and time. Every point in all of space has a certain value of electricity and magnetism, right? It has an electric value and a magnetic value. Those values are at right angles to each other. They're what we call orthogonal. And what we want to do is we want to induce a wave in that electromagnetic field that will travel from one point to another. And so when you talk on your cell phone, what your cell phone is doing, it's inducing this wave in space and in time that travels to the cell tower and then travels back. Fundamentally, they travel at the speed of light. It depends on the medium they're traveling through, but we assume it's the speed of light. And then the frequency and wavelength, these are two inversely proportional values for an electromagnetic wave. So this little diagram here, so you can see that when we're at low frequency, we have a longer wavelength. Higher frequency, we have a shorter wavelength. Typically speaking, the lower your frequency, the longer your wavelength, the easier it is to get it to travel a further distance. But you're also going to be limited a little bit because unfortunately, those low frequencies, a lot of people have grabbed up pieces of them. When you communicate over an RF carrier, you're going to have to license not only the frequency that you're transmitting at, but the bandwidth that exists there. If you think of it like a bar, right? This is all the electromagnetic spectrum that's out there. You're going to grab a sliver of it. Unfortunately, at those lower frequencies, all those slivers have pretty much been taken. And so it's a lot harder to get frequency in the lower spectrum, but lower spectrum is better for longer distance communication. So it's a trade-off. So like I was saying, the electric field and the magnetic field, they're perpendicular to each other. Generally, when we polarize an antenna, we polarize it with respect to the electric field. It doesn't matter that much, but just for your cognizance. Here's some of the common frequencies that we talk on. We give them these sort of letter and acronym designations so we know what we're talking about. So if I say, oh, this is an S-band radio or this is an S-band antenna, I mean, it's talking over this frequency. And this gives you also the rough data rate that you can get at that frequency as well. And then when we talk about like VHF, that stands for very high frequency. UHF, ultra high frequency. I guess when they first invented radios, they thought you'd never get beyond ultra high frequency. They thought that's as fast as it'll ever go. No, it goes a lot faster. So impedance and matching. This is something when you design a communication network, when you design lines to connect to radios, to connect to antennas, something that's also important is that you want your impedance to match. In electrical engineering, we take a fundamental circuits class, right? One of the first things we learn after Ohm's law and after KVL and KCL is phasor domain, right? You learn what is phasor domain, how do you represent it? And what that essentially is, it's you take a signal, right? A voltage signal that goes up and down, right? And you just treat it as a constant. And you'll find that certain electrical components, they act weird when you get into voltage going up and down. They don't quite act how they do when you just apply a DC current to them. Basically, depending on the frequency you're at, you're going to have what's called an impedance. And that impedance is essentially the sum of all these effects that occur from all the electrical components that I suppose look like resistance or act as resistance or an impedance to your current. Does that make sense? Hopefully it does. Super clear. And it's important that in a communication system, your components, they're all impedance matched. The reason you do that is because you have a mismatched impedance, you'll get what's called a reflection. And that reflection back, it makes it so your network doesn't really work as well. In fact, it can completely stop it from working altogether. So something critical, something you need to be aware of. Most of the time, the impedance that we baseline is 50 ohms. Those electrical engineers or anybody else, by raise of hands, how many of you have taken like microwave engineering or something of that nature? No? Okay. Well, if you ever take that class, you'll learn all about that stuff and much, much more. So now we've talked a little bit about the fundamental field and the components. Let's talk about what it is that we're actually doing with this electromagnetic field and what it is these components are actually doing. So the way we transmit information using a signal is something called modulation. Modulation is a way that we manipulate that carrier in order to detect the information that we transmitted. And so I'll get more into this later, but just be aware modulation is a term that we use and we'll be using it a lot. Some examples of modulation can be amplitude modulation or frequency modulation. That's AM, FM in your car radio. Some other examples that can be used are things like phase shift keying. So basically you take information, right? It's usually in binary, zeros and ones, and you chop them up into different phase shifts, and you can detect those phase shifts on the receiving end and sort of backtrack what you did to that wave to get that information out of it. And that's something really reliable. In fact, the vast majority of satellite communication is going to be using some sort of phase shift keying. Sometimes I've seen Gaussian mean shift keying, or if you're doing like optical comms, you'll have something called on-off keying, but the majority of the time you're going to have a phase shift keying. And then the data rate, this is important. This is sort of the fundamentals of digital communication, which is what I'm getting my doctorate in, by the way. The data rate at which you can reliably transmit data is always limited to your bandwidth, period, end of story. And so that's the reason why when it showed that graph, if we go back to this graph isn't totally actually accurate. What that's saying is your likelihood of getting that bandwidth, right, to get that rough data rate is higher as you go to higher frequencies. But the carrier frequency isn't what actually governs your data rate. It's your bandwidth. And the fundamental band limited channel equation that you will see all the time is right here. That was developed by a guy named Shannon in the 1960s. And that's basically like the E equals MC squared of communications. Very big deal. And what this is saying, this simple little equation, is if you have any type of channel with any type of bandwidth, you will always be able to reliably communicate over it, period. End of story. That's weird, right? You wouldn't think that, but it's the truth. That he proved it doesn't matter how noisy your channel is. If you have the channel, right, you will always be able to transmit some type of information over it. I'll ask a question. How about that? All right, the Viking 1, right? Satellite very far away from Earth. Will it ever reach a point where we cannot get any data onto it? Like you can't communicate to it anymore. It just gets too far away. We'll always be able to communicate to it, but however, practically speaking, there will become a limitation to how long it takes, right? At some point, you'll have to spread out your information so long that it takes 4 or 5 infinity years to talk to it. So practically speaking, yes, there will be a time where we won't be able to communicate with it in a reasonable amount of time, but we will always be able to transmit some type of data to it. Does that make sense? The information, it will go slowly, right? Eventually we'll reach the point where we can't put more power than the Earth has capacity for into a ground station to talk to Viking 1, and it take longer than 4 or 5, some ridiculous amount of time. So in terms of that, practically there will be a limit to when we can communicate with that satellite. However, theoretically, there is no limit. Theoretically, we'll always be able to send something to it. It'll just take forever. I'll just give you a brief overview. We're not going to spend too much time on these slides, but it is important that you understand that components that go into the space vehicle side of the comm system, components that go into it are something that are design decisions that you're going to be making. So just so you're aware of them. Typically, you're going to be matching your space vehicle side with your ground side. And so obviously you want them to respond to the same frequency. You want them to be matched in terms of the protocol they're going to be communicating, stuff like that. Typically what we'll see in the hardware on the space vehicle side, your antenna, that's a very important one. The transmitter or receiver, sometimes, a lot of the times they're combined into 2. We call these a transceiver. Your RF connectors, your cables, stuff like that. They have all sorts of different connectors, SMA, MMCX, micro FL. The majority of what we like to use is the SMAs. They're a little bit bigger, so they're kind of harder to fit into a small satellite, but they are much more reliable. So it's like, if you can design your system to use that type of connector, we recommend it, but it's not critical. We've flown those other connectors as well, and they work fine. And then sometimes you'll have some inline amplifiers or splitters. Typically we do this, if we have antennas that perhaps they have like half a radius or half dome coverage, right? But we want full dome coverage. Like sometimes you'll see satellites put 2 of those on either side, and then they join them together with a splitter in the center. And then the ground hardware, obviously you have your antenna dish, your Yagi, if you're building your own ground system, or you want to be aware of it if you're hiring out your ground system to some commercial provider. So let's talk a little bit about what an antenna is. An antenna is kind of a cool little device that what it does is it sits in space and time, and it will react to the electromagnetic inducted currents that travel through that exact field, right? So again, electromagnetic waves, they're just waves in a field, and that field permeates everything. So as it sits in that point in space and time, when a certain electrical field is incident upon it, it will induce a small amount of voltage basically on the output of that antenna. We can tune these antennas and we can design them that they will resonate very highly at frequencies we care about, right? And that they won't resonate very well at other frequencies. So some of the things we want in an antenna, we care about the impedance that we talked about before. We care about the capture area. Obviously, on the space vehicle side too, something that we care about is the complexity of design too. It's like you'll have antennas that they'll tout all sorts of gain figures and they'll be amazing, but you're like, how on earth are you supposed to get that aboard a satellite? Some of them are impossible to get aboard a satellite unless you had like a really big satellite. With small sats, you're probably never going to get a dish on a satellite unless it's some sort of deployable. You're never going to get some type of satellite dish, but there are different deployables that, such as whips that are more practical. In fact, they sell them commercially, and they're just these whip antennas that they kind of look like a turnstile on top of your satellite. And so that's something that's a deployable that has worked before in the past. So yeah, a couple of different types of antennas. You'll see the dipole ground plane. That's sort of, if you ever take microwave engineering, that's the basic antenna they'll first teach you about. This little guy is this little hook looking guy. What is that? Is that a harpoon hook? No, it's an antenna. It's kind of cool. The majority of what you'll see on satellites are typically some sort of patch, right? So your GPS antennas, the majority of them are patches. And then there's helix antennas. We don't typically fly those. We have before, but again, they have to be in some form of deployable, and they get tricky, right? Because it's a very complex deployable. But they do exist, and they have a pretty good gain figure on them. An important thing about antennas is they'll have some sort of pattern like this, and the gain figure, typically it's represented in dBi, and what that stands for is decibels with respect to an isotropic radiator. So isotropic means it radiates in all directions like a giant sphere, right? And then the, I guess, ratio between how it actually radiates between those 3 decibels of margin right there and that isotropic radiator is the gain figure. That's the dBi. So, 9 dBi gain, that's a pretty decent gain, right? And typically the more directional your antenna goes, right, the more you focus that electromagnetic energy or the induction of the electromagnetic field, right, then typically your dBi is going to go up, but your directivity, it's going to go down. And so again, this is an important design decision, right? Because you have a satellite, right? It could be tumbling up in space, right? And it's like, if you have a highly directional antenna, it's like your chances of being able to reach it, it's like you just hope that, hey, I hope the bore sight of that antenna is pointing at my ground station the exact moment I want to talk to it. That's not a very good guarantee, right? And so a lot of times we want to go for something with a lot less directional, something that you can contact from more angles, right? More opportunities. A lot of times on different satellite programs, we need to be able to close the link from any direction. So 4 pi steradian, right? So the entire sphere shape, we want to be able to close the link at any point. The reason that we choose 1/4 of the wavelength is because in order to induce a current to resonate with a frequency, it needs to be proportional to the wavelength of that frequency. That's a really good question, actually. In fact, the longer it is, the better it'll resonate, but we need at least that 1/4 wavelength long. And the reason that is basically, if you think of, for example, like a dipole antenna, it's a prime example, right? If it's at least a 1/4 of wavelength long, then at one end, right, it'll have the most positive peak of your signal, right? And at the other end, it'll have a 0, right? So that's the way that it'll resonate. Anytime you design an antenna, you're typically designing it to a carrier frequency, and you want those antennas, specifically, I believe this one is talking about monopoles and dipoles. You want them to be at least a 1/4 of a wavelength long in order for them to correctly resonate with the frequency. So again, your gain versus your beam width is always going to be trade-off. The more gain you get, the narrower your beam width. So this is just some information a little bit about the resonance that occurs in antennas, how that works. So not all antennas will resonate. In fact, there's going to be some that are called non-resonant antennas, and they're not going to be some multiple of a 1/4 wavelength. And these are hard to design around because it's hard to impedance match them. It's hard for them to be able to induce the current that you want. Because of that, we really want to design a resonant antenna, or we want to purchase a resonant antenna. So antenna patterns, we talked about how we can have an isotropic pattern, right? So this would indicate a 0 dBi gain, right? So that means it isotropically radiates. This is sort of your theoretical antenna, goes out in all directions. So this is something we'll get into, but it's important when you design a communication subsystem that you understand that there's going to be a trade-off between your directionality and the amount of power you're going to be able to receive at the end. Why is it that light is less bright when you're further away? So what Nathan just explained was that when you transmit light, there's some certain energy density that's in that light, right? It's a concentration of photons specifically. And so as it travels outward, those photons, they become more spread out. When you see a light that's, say, 10 kilometers away versus 10 meters away, it's a lot less bright because that intensity, that power, a lot less of it is incident on your eyeballs. Literally, antennas and RF waves work the exact same way. So when you radiate from an antenna, right, if it's radiating in all directions, then your ability to receive, it comes down a lot more, right? Because that power density that you transmitted, most of it goes out in directions you don't care about, or you don't have antennas, right? It's like you only have one antenna somewhere. And so that's the reason that it's going to be a design decision where you're going to want to close link with your satellite at any direction. Keep in mind that having all those directions means you're going to have a lot weaker signal, which means a lower signal to noise ratio, which means lower capacity for the channel. So dipole antennas, this is something that it has a bit more directionality to it, a bit more gain, but it kind of radiates in this torus shape. The gain there is about 2.15 dBi. Helix antenna, so these are much more directional, and they have gain figures from as low as 3 to as high as 24 dBi. 24 dBi, that's very high. That's like 100 times, over 100 times, over 200 times what your isotropic radiator can do. So highly powerful, but also highly directional. There's another type of antenna, kind of a pokey looking guy, canted turnstile that can have a near hemispherical shape, some horns. So that's what you'll see on a receiver dish. So when you see a ground dish, that dish just acts as a reflector that feeds into a horn. And then the horn is really what the antenna, that's what's radiating and receiving and resonating. Polarization. So this is something that's also important. When we transmit through the electromagnetic field, we transmit with respect to some type of polarization. What that means is basically when the wave is going a certain way, that electric wave is what we polarize against. So when that electric wave is going up and down, that's a certain type of polarization versus going side to side. Does that make sense? When you align an antenna, you want to align with that polarization, because if you have, for example, a vertically polarized wave and you're trying to receive it with a horizontal antenna, you're not going to receive anything, right? It's going to induce no current on there because the electromagnetic field at that point in space is completely orthogonal to what it can induce in that antenna. Another type of polarization we use is something called circular. And what that does is, instead of resonating the electromagnetic field in one straight line, it alternates basically. It does it in a circle, right? If you look at the wave, it's like the wave twists almost, kind of like a churro. And so you can twist it in right hand or left hand circular polarized fashion. And same idea, right? It's if you have a right hand circularly polarized antenna, right, but you're trying to receive a left hand circularly polarized signal, you're going to basically receive nothing. Essentially, the loss is going to be theoretically infinite. It's not actually infinite. It's usually like negative 100 dB or something like that, but it's large. You're going to have a very large loss. So large that you're probably not going to be able to receive your signal. Now, here's the weird thing. You can actually mix and match. You can do vertical antenna with a right-hand circularly polarized signal, and you can still receive it, but you're going to take a loss of 3 decibels. So you're going to receive half the amount of power that you would have otherwise. So it's like you can mix and match them, right? But yeah, you got to be aware that there are certain matchings that won't work. There are some matchings that will, but you will take a hit. So the best thing to do is to just match outright. And what we typically transmit in space, especially in low Earth orbit, is going to be some sort of circularly polarized signal. So you're going to want a matching antenna for that signal. Here's some choices. Typically, you're going to be bound to some sort of patch or a whip if you're flying on a small satellite. That's just realistic, given that you can sort of mix and match your signal with the polarization of that whip. If you can get the link to close, and I believe UNP requires a link margin of positive 6 dB. If you can get it to close, then you're still okay. That's essentially what I was explaining before. So let's talk about the actual hardware here. What the hardware does, this is what connects to your cable that connects to your antenna. So the antenna, it induces a current That current travels through that impedance matched cable to your transceiver hardware. And the transceiver hardware, for lack of a better term, that's where the magic happens. That's what does all your signal detection and all your demodulation and modulation. They're cool little devices. They can be very complicated too. The transceiver hardware, it's responsible for all the functions to reliably transmit and receive data. As we saw in the Shannon formula, we know that as the noise to signal ratio goes up, your ability to transmit data, right, reliably, that capacity, it goes down. And so we need to attune for that somehow. That's part of the functionality of this transceiver hardware. Also, it handles command and telemetry data. It'll hand that over to your CNDH subsystem. That's your main flight computer. If you need your satellite, you say, hey, you need to turn this way, or hey, you need to point to the sun, right? It'll handle that data. These subsystems, they provide both the RF interface to your antenna as well as the software interface to that radio. So they're sort of the translating layer in between. They can be hardware based. In fact, the majority of radios I've seen people fly, especially in UNP, a lot of them are hardware based just because, they're a lot more reliable. But unfortunately, when they're hardware based, you're kind of stuck with the architecture they give you. There's another type of radio that's called software defined radio, an SDR. It's software based. What that means is basically it just samples the signal that's coming into the antenna and then gives you those samples and you deal with it. That's essentially what it means. Software defined radios are cool because you can adapt them to whatever waveform you like, but they are also really hard because communications is hard and it's a lot of signal processing stuff you don't normally need to worry about that you do with the software defined radio. Now, most of the time, you're going to have some sort of combination of the two. So you're going to have some sort of software hardware defined radio. Sometimes when you buy a software defined radio, what they'll do is they'll give you a software defined radio, but luckily the company that gave it to you, they also give you all the firmware and software to make it run. So you don't have to worry about it. Now, don't take that as a given. That's not always true. Sometimes they will just give you the piece of hardware and they're like, you deal with it. And again, this is something you need to be cognizant about when you decide on which transceiver board to buy. You have to know exactly what is this coming with. Does this come with software? Does this all rely on me to make? And if it all relies on you to make, more or less you're in trouble because it's really hard to get these things to work without a very extensive background knowledge in a lot of different fields and theories. Sometimes they'll come in bare boards like this. Sometimes they come in a little aluminum enclosures. It doesn't really matter. The aluminum enclosure is nice because that way you can kind of test it on like a bench top and not worry about ESD events. However, they'll both work more or less the same. The selection of this board, you have to take a lot into account. In fact, I would argue that this is probably one of the most, if not the most important selection that you'll make is on the transceiver board that you purchase. Or if you're designing your own, good luck. Some of the things to consider: software development, like I was talking about. Is it a software defined radio? Do I have to actually create all these functions that interrogate the signal, pull it apart and equalize it, and do clock recovery and phase recovery and frequency recovery? Like all these functional blocks that all have multiple papers written on them. It's like, is that going to be your problem, or is that already provided for you? So that's something you need to be cognizant of. Obviously, you need to be cognizant of the power. So every radio will have two different power levels, right? They'll have two different power numbers, right? One is the amount of power it needs to run. That's in watts. It's like, oh, this needs 10 watts to run, even to turn the board on, right? And then there's a radiating power, right? And that radiating power is the one that you care about in terms of your link budget. So how much will it radiate, or how much power? That's typically in a number called dBm. What that is a ratio between the actual output and 1 milliwatt. So that dBm number, right? That's what's going to be feeding into your antenna. Your antenna will focus it, and then that'll go to the ground. That's essentially how you build a link budget. We'll get into that a little bit more later, but it's an important design decision. And then obviously, what's its periodicity? What does it store? Some of these smaller things that you may be concerned with. How does it handle commands? That's something that, you need to design an interface for it at some point. How hard is the interface to design? How well is it defined, the API? right? That's something you want to look into. And then last, but also very important, is frequency licensing. What frequency does this actually talk on, right? What does it actually transmit? What are my likelihood of securing a license in this frequency? There are some bands that I discussed at the beginning, they are much easier to get licensing for than others. In fact, there are some bands, they are basically impossible to get a license for. And you don't want to be stuck in some bureaucratic mess for years and years while your satellite is sitting on a shelf gathering dust because you can't get a license. Nobody wants that. And then also, I've mentioned this multiple times. I'll mention it again because it's very important. Be really careful assuming that your transceiver is just plug and play. Some of them are, most of them aren't. Most of them, they take some sort of software at minimum to interface with it, right? And that's something that you need to take into account when you do your system design. In fact, if you choose some radios, the software design overall is just so extensive, there's no way you get it done, depending on the size of the team, less than like, I'll say 3 or 4 years. I mean, they can be that bad, you know? So again, be careful. And I'm not saying this to be glib. I'm not saying this to be, you know, say like, oh, you don't know this. It's like, I've met industry professionals that have made this mistake. I've been on programs where people have made this mistake. They assume, oh, I buy the transceiver and I just put it in and it just works, right? And then they plug it in and it doesn't just work. And then they're like, oh, now what? We just wasted so much money. Like I'm telling you, this happens. And so it's be really cognizant of what you're getting with your transceiver board. So let's go a little bit over the CONOPS. Before that, does anybody have any questions? The question was, for those of you who can't ask, basically if there's a mismatch between, say, you have a circularly polarized signal and a vertical antenna, you take that 3 dB hit. What does that mean in terms of how much information you can gain? Does it take longer? So theoretically, it would be an information hit. However, practically, it probably won't make a difference. And the reason that is because a lot of times these transceiver boards, they'll be built in with some sort of architecture that assumes a minimum sensitivity. And what that means is you're going to be able to meet this sensitivity figure at the end of your link, right? So when you concentrate that power through the antenna, it travels the path loss that Nathan talked about, and then you receive it through that gain, and then it goes through that cable, right? You sort of complete that whole loop. When you receive it, it'll give you a number saying you need to receive at least this many dB in order for this radio to function. And a lot of the times, if you take that 3 dB hit, it already assumes that sensitivity. And if you meet that sensitivity, then it'll work the way it was intended to work. And a lot of these radios, they're built in with, most of them with some sort of fixed type of modulation and coding. And so the data rate they can transmit, that's all you get. There are some different kind of radios that are smarter. There are some that can switch modulations and codings. This is something, for example, that satellite TV does. So DVB-S2, that's the standard that you use to watch Dish or DirecTV. None of you guys watch that stuff because you're all young and you watch Netflix. I don't either. None of us really use satellite TV anymore, right? But it still exists. My parents still watch satellite TV. That's something it uses, right? And it has a standard that it can transmit different modulations and codings depending on the sensed power that it's receiving. And so it's a little bit of a smarter radio. Most of the radios you're going to see for small satellites are not that smart. They're going to be fixed with a fixed modulation and coding, and the data rate it can transmit, that's all you get. So let's go into the CONOPS, what it takes to talk to a radio. The other thing you need to consider is what kind of data rate do you need? How much data am I generating aboard my satellite? And how often do I need to contact this and offload that data? That's going to be a big design decision into, hey, this is a transceiver board that can transmit 5 kilobits per second versus megabits per second, right? Or if you need a whole lot of data, you know, it's like you might, I've seen this done on multiple satellites before, and it's something that's pretty effective. A lot of times it's like, to command and handle telemetry, we don't need a lot of data, but our payload, right, our experiment, it generates a lot of data. Like say it's generating images or you know, capturing high definition images, you know, in space, right? It's like, that's a lot of data and I want to get it off the satellite. So a lot of times they'll use like a lower data rate transceiver just for handling telemetry and command. And then they'll use a very high data rate just transmitter in order to say, hey, point this transmitter at the ground station and then just start dumping your data. And that's a pretty effective architecture I've seen work on a lot of satellites. Obviously, we talked about meeting licensing, legal requirements. So some of the COMM data requirements that we care about, some of the things that your satellite may do, they may transmit, housekeeping science data. They may beacon. Beacon is something that is essentially like, it's like a heartbeat saying, hey, I'm still alive. Here's my status. It's something that it may do that you need to take into account because it will take a impact on your data budget. You need to accommodate uplink data in specific amounts and intervals. So again, like how often are you commanding this thing? What are you doing with those commands? What's the data density, the information density of your commands? These are all things you need to take into account. Obviously, you need to close link, that's uplink and downlink. And what I mean when I say closed link, I mean basically that you meet that sensitivity level within the margin that is specified. Specifically, we specify a 6 dB margin for UNP. It's a really good one. It's not too hard to meet on low Earth orbit. If you're doing satellite in cislunar space, it's much harder. But in low Earth orbit, typically it's not too hard to close link. And then obviously you want it to deploy safely. So if it's a deployable antenna, it's like how likely is it to fail? If it fails, am I just out of luck? Can I just not talk to my satellite? Or, what's the backup plan? This is all stuff you need to consider. The moral of the story of this entire event should be that systems engineering is critical. These are all design decisions that are made by systems engineers at the very beginning, and they will all impact whether or not that mission will close or whether or not it will go forever. I've seen many missions that had poor systems engineering at the beginning that just went on forever. And it was not the fault of the people on the team trying to get it to close, even though they felt like it was their fault and they were the ones getting kind of yelled at, right? It wasn't their fault. The fault was wholly at the beginning, at the concept design level, at the very beginning. That's the reason we're presenting this stuff to you, is so you understand. So yeah, these are all the things you want to take into account. They're all stuff I've talked about already, so we won't spend too much time on it. So the comm stack, this is a section that it's important, but it's not critical. The reason I'm telling you this is so you're cognizant, again, of how does the underlying communication work. So when you see things like, oh, this uses QPSK with a 1/2 BCH coding, what does that mean? Like, why should I care? This is all stuff that you need to at least be cognizant of, because they will change the characteristics of your radio, as well as those system design pieces we talked about, how long it'll take to develop software, whether or not you can close the link. All that depends on what we call the comm stack. So what is the stack? What am I talking about? So the term actually comes from an old OSI networking model that talked about how you communicate between two computers. And so typically what you do between two computers, you have an application that your user is interfacing with, or something on your computer is interfacing with. And what it'll do, it'll kind of dive down what we call the stack into different data units in order to become either electromagnetic radiation or a signal over a wire. And so this is a term that's kind of been hijacked a little bit by a lot of us who do comms design, because when we say, oh, this really only reaches layer 2, layer 3, people will know what we're talking about. And what we're talking about is essentially these layers of functional application. Given the functional domain of the application, typically most satellites, they'll really only ever go from layer 1 to layer 2. Unfortunately, these radios, when it comes to these higher layers, it's not really critical. We don't really need it, for one. And two, it just adds more complexity. Now that's poised to change. There's a lot of efforts that are going on right now to get satellites to talk to each other in clusters. Think of like Starlink, for example, right? It's like you need to have some sort of method of, routing data between satellites because they have crosslinks. That's where you're going to start to see more of these layers sort of take hold. But for the most part, you're only ever going to see up to layer 1, layer 2 on most satellites. So the physical layer, that pertains to the hardware that we talked about. So again, antennas, coaxial cables, right? Your transceiver. Typically, the fundamental data unit you can think of are bits and symbols and, I don't know, waves. It's all has to do with, I guess, the physical. How do you turn a bit into information over a wave? That's all in the domain of the physical layer. The data link layer, these are functions that ensure your link's integrity. So make sure that, oh, when I break up my data into a frame to split into bits and send, right? When I get that frame back, how do I know that frame's correct? How do I know that one of the bits didn't get flipped? You don't want to feed bad data into your computer, into your CNDH, because if you feed just bad data into your CNDH, all sorts of weird things could occur. You don't want to do that. So it ensures that they're correctly received. It also ensures that, hey, I'm reconstructing, all my frames of data back into this sort of larger packet, if you will, that was sent to me originally. And that's the function of the data link layer as well. And then there are more layers, more functions that are added to more different satellites and different architectures, right? But the data link layer, the entire stack in general, it's written as like kind of these solid, like, oh, this is the boundary of this is the boundary of this. But more realistically, there's a lot of sort of gray area in between. There's a lot of stuff that you're like, oh, that's physical layer. No, that's data link layer. It's an argument. So let's talk about the physical layer though. So the physical layer, these are radio waves that are incident on a antenna, right? They'll cause the antenna to resonate. That's filtered and amplified into some sort of electrical signal. Clear enough how that works? Typically, the wave will look something like this blue wave, right? That travels through space and time. Now, what I'm showing here in these figures that I think is very important that you understand. In fact, it'll help you understand, I guess, the entirety of the physical layer, specifically when it comes to phase shift keying. So those smaller waves right there, those are actually all added together to make that larger blue wave. So you take a bunch of waves that are shifted in frequency, you add them together, you're going to get another wave. In fact, you can keep breaking it down. You can just get more waves, add them together, and they'll make another. You add them all together, they'll just make another wave, right? But you see, the more you add, the smaller their amplitude becomes to add. If we constrain that larger blue wave to be between 1 and -1, right? Then if we want to split up that wave by multiple frequencies, you'll notice those waves, they're getting shorter and shorter, right? In fact, you can just keep doing it and doing it and doing it. Eventually, those waves will just become a bunch of flat lines, right? That somehow add together to a wave. So every wave is actually just an infinite sum of flat lines. It makes perfect sense. No, it's just a point where math kind of breaks down. So this is the fundamental concept behind phase shift keying, that you can break a wave into multiple phases, right? But you're going to take a penalty. In fact, if you have waves that are too small, if you're transmitting over noise, the noise is just going to drown that out, right? And so there's sort of a weight between choosing, okay, how many phases am I going to, I guess, embed in my signal versus what is my ability to, I guess, pull that information out from those phases. Those are all stuff you need to take into account. And these signals, right, that has all this phase information that we care about, they're going to be sampled and quantized by an analog to digital converter, and these become digital signals. Digital signals are really just information. It's really just like data, right? So it's just a bunch of numbers, but we typically represent them as sort of like vectors, right? They're kind of like a wave, right? The magnitude, I don't have a figure here. They're digital signals. There's multiple corrections that we have to do with these digital signals because they're just taken at some point in space with some amount of noise. We need to recover them in such a way that they are representative of what was transmitted. And these corrections can include clock recovery, phase shift recovery, phase recovery, frequency recovery. These are all things that need to be done before you demodulate a signal. And they're also very complicated. And these are sort of the functional pieces that can make or break whether or not your radio works correctly. And unfortunately, in a lot of radios, like the hardware ones, you don't have much control over them. You trust that whoever designed it, they designed it correctly. And then demodulation occurs. So what we do, basically take this wave, right? We all know from Euler's formula that we can represent a wave as a complex number, right? Specifically e to the I, j, or e to the j frequency, whatever, theta, right? If we sort of assume a constant frequency, then we just care about that phase component, right? So then we can map in what we call complex phasor space, these signals, right, that are sampled at a certain period of time. And when we sample at a certain period of time, we can see, oh, look, the phase is shifting depending on when I sample them, right? And those phase shifts are what we use to embed our data. Here's, a classic mapping of, oh, whenever I see something that's at this phase, I just assume that's a 1-1. The opposite is a 0-0. This is what we call QPSK, or quadrature phase shift keying. It's just a way we embed information into a wave. Again, there's other ways to do this too. We could use binary phase shift keying that just does 180 out, right? So it's like if the wave flips upside down, I assume that's a 0, and it goes back up 1 0 1 0, right? That's a very common one as well. There's other type of modulation too, but these are some of the more common ones. And so when you demodulate, it's going to result in some sort of binary output. With that binary output, typically what'll happen is you'll do what's called channel coding. So channel coding is a very complicated topic as well. It has to do with information theory. Specifically, channel coding is trying to overcome the noise of the channel. Technically, what it's doing is it's trying to maximize the mutual information between what was sent and what was received. That mutual information is it's a mathematical quantity. If you ever take information theory, which I recommend, it's a really good course. It's a really good subject. You'll learn all about information entropy. You'll learn all about mutual information. You'll learn about not only channel coding, but also source coding. So that's like compression and stuff like that. So like how you compress files in your computer, you'll learn how that's done. So channel coding, this helps to detect and correct any errors, any bit flips that occur in that binary stream that was applied. You can remove that, and the resulting information is the binary that you sent in the first place. So what you take out of demodulation isn't necessarily the information that you sent. It's just these sort of source code symbols that you then have to map into the information. We'll check the integrity of those data frames, determine it with some sort of end of the frame checksum is typically how that's done. Any failed checksums are assumed to be a bad frame, and then you request retransmission. And then the frames, they're assembled in the correct order, and they're authenticated, usually using some sort of link layer security protocol. This is done for media access. The reason we do this, and it's important, right, is like if some hacker somewhere got a hold of the spec of the radio, guess what? They could just inject data frames into your radio. And if there's no like control access, right? There's no media access. Guess what? Radio will be like, oh yeah, that's a valid frame. Go ahead. You're good. And they can put all sorts of bad stuff onto your satellite that you don't want. And so that's something that we build in typically at this layer. And then delivery is facilitated. A lot of times this is specific to a standard called CCSDS, but delivery is facilitated using some sort of virtual channel field and a transfer frame. What that really just means is, oh, I know where this is going, which application, so here's sort of the address. It's sort of like a rudimentary routing protocol. By the way, you'll commonly see radios, some of them will be like, oh, this is CCSDS compliant. What that means is it implements some sort of CCSDS link layer, and a lot of times the space packet protocol in the radio itself. So it can be really useful. The standard itself, if you're ever looking for any light rating, I think each section there's I want to say there's like 5 different data link layers, and then the space packet protocol, right? Each one's about 200 pages. So if you ever just are bored, they're all online. You can read them if you're that curious. It is a standard that you'll see a lot on space-based communication. I think this is the last section. A little bit of the analysis that we do. We talked about the link budget. So the link budget is really what's going to be ruling, I guess, your life in terms of systems engineering. What you're essentially going to be doing with a link budget is you're just going to say, hey, what are my gains? What are my losses? And does it reach the sensitivity with the margin that I care about? That's all it's doing. Link budgets are actually pretty simple. All you essentially do is you just follow the link right from transmission. Oh, it's spitting out this many dBi. I assume this type of cable loss. Oh, but I get this type of gain for my amplifier, plus this type of gain for my antenna. I get this much loss from my path, right? Then I get more gain from my receiving antenna, right? So you're just tracing the entire path. And then you see at the end, okay, what's the final number, right? And is it more than 6 dB over the sensitivity? That's essentially what you're doing, and that's pretty much it. There are some flavors of link budgets where instead of the SNR, you'll do what's called EBNO. That stands for the bit energy to noise ratio. And that'll take it even further. So that'll take into account like your modulation and sometimes your source coding. And that'll say, okay, what's the exact sort of number that I care about, right? In terms of how much energy do I want sort of packed into the bit, right? The thing that I'm transmitting. So it's essentially a flavor of the same thing though. In fact, it's actually fairly trivial to switch between an SNR figure to an EBNO figure. There's multiple, formulas and ways to do that are available online. It's not too hard. Another test that you'll do, I believe this is one that's required by UNP, is an antenna pattern testing. Sometimes the antenna will claim a certain pattern, but it may be off by a little bit. You just want to verify that, because if you built your entire link budget based on, oh, this is definitely what my pattern is going to look like, and it looks like something different, you want to be cognizant of that. So this is an analysis you want to do. And then a full range COMM system test. Something that we do is something called a long range and a SimComm test. And so we talked about the antenna pattern, and then there's the long range test where essentially you will basically build your link end to end, and then you'll test, hey, can I actually get data through this link? That's an important one too, right? Because it tests every single piece in that chain. And when you can close that link, you can be more confident that, hey, my comm system is going to work on orbit. That's all I've got. I would love to hear any questions. If I were on a team that was purchasing a radio, I would do everything I could to get every single data sheet, every single API from them before I promise them any money. And sometimes that can be hard, right? Sometimes that requires, oh, well, some of this stuff is proprietary. You just go back at them. Fine, I'll sign an NDA. That's fine. Like, I need to know as much information as possible in order to know what the effort is going to take in order to develop. Because again, it's like I've seen radios like this that go on small satellites that literally they give you the hardware and they're like, you design everything. You program the FPGA, you load the operating system onto the microprocessor core, you write all the software to interface. It's like, we just give you the hardware. And it's like, you don't want to be stuck with something like that. I've also seen radios too that they'll say, oh, this is something that has this very intelligent routing protocol, or you're made to believe that way. But then once you talk to them, they're like, actually, it's just you dump your data into a buffer and then it sends it. It's like, oh, that's not at all what I thought it was going to be, right? Now, for some applications that may be okay, but it's really just about being cognizant of, okay, what does this actually implement? And a lot of times it's like, if you just look at like the marketing brochure, it'll say something like, oh, this implements CCSDS protocol, right? Well, CCSDS is like saying, oh, it implements IEEE. IEEE what? It's like there are so many different standards defined under that. Same thing with CCSDS. So it's like, be cognizant of what standards exactly and what those standards mean in terms of like what you have to develop towards. It's not impossible. It's not undoable. And it's just something that takes a little bit of initial effort and initial research. A lot of times, given the stuff I presented, you'll be able to gauge pretty accurately like, oh, this is going to be fairly minimal software effort versus this is going to take forever. Software-defined radio is one of those loosely used terms that people sort of sprinkle on because it sounds cool. A lot of times with software-defined radio, what you'll find is it's actually more hardware-defined. So for example, let me go back. So this guy right here, they market that as a software-defined radio. But in reality, what it has right there is a Zinc 7020 that interfaces with an AD9364 transceiver chip. So that if you're familiar with Velcro architecture, it's essentially that transceiver chip, it just takes IQ samples and then it'll filter them and send them through an A to D converter or a DAC converter, right? A lot of what's actually on this isn't really software defined, right? It's like an FPGA, right? It's more firmware, if you will, right? It's more reconfigurable hardware. The transceiver chip, you have no control over that other than, oh, what filtering coefficients am I sending through it? They'll market things like that as like, oh, they're software defined, but really like a pure software defined, in my opinion, is literally it sends the IQ samples to your computer and you deal with it in a microprocessor architecture. The Zinc 7020, it's what's called a system on chip. So it has an FPGA, but it also has an ARM core. That microprocessor core, you'll define some of the functions, right? But most of them will be in hardware. Does that answer your question? They're not all that way, by the way. Like if you ever use like an RTL dongle, that's basically purely software, right? It's like it'll give you a fighting chance with the IQ samples, but your computer has to keep up with the data rate that it's streaming. The answer is it's a mixed bag. Good questions. Any other questions? Yeah, so let's go back. When we talked about this, typically the way that we measure our antennas are by a 3 dB beam width, or that's the same thing as saying a half power beam width. So 3 dB is the same thing as 1/2. And so when we measure that 3 dB beam width, and then we say, okay, what's that ratio to our perfect isotropic radiator? That's how we get our half power ratio, right? It's in dBi. That's a great question. Are there any other questions? Strangely enough, price wise, I guess it depends. It's like I'm used to working in programs where price isn't much. I shouldn't say it's no figure or whatever. It is a figure, but it's not much of a figure. So in terms of the price, there is going to be a difference, but surprisingly, you'll find it's not that big of a difference between those like turnkey solutions versus, oh, we developed this hardware. There is going to be a price difference, right? Obviously, they want to recover the costs of, hey, look, we had a bunch of engineers develop this stuff. We want to recover their time and the cost into that versus, oh, we just had the engineers design the board and that's it. So there is going to be a cost difference. I would say in rough orders of magnitude, you're probably going to see like a 40% cost increase. It's probably a good round number. Sometimes you'll see more, sometimes you'll see less. That's a good question though. Thank you very much.